Kia ora Year 12. This is the second complex numbers video for people away tramping, and this looks really horrible, but actually it's not too bad. We're going to solve a quintic equation, which is a polynomial of degree or order 5. So this is the question that I've picked out. We need to solve that, and we're not given any clues at all. So let's think about how we're going to attack it. Well, the first thing we're going to do is we're going to hope like crazy that using the factor theorem, we can guess and check our way to at least one factor, and that will then let us get down to a quartic. The other thing we know is that the complex roots are going to occur in conjugate pairs because we've got real coefficients, not complex ones here. So that's going to help me, but it doesn't give me a starting point. So to get going, what I'm going to do is set up that polynomial as p of z, and then I'm going to start picking factors. So you might want to pause the video and just see how far you can get through on your own. You definitely don't have to watch the whole thing. So we're going to start with 1. Let's try z minus 1 as a factor. So p of 1 is 1 minus 6 minus 2 plus 17 minus 10. So adding that up, what do we get? Yep, we're very happy because we've got 18. Take away 8, take away 10, which equals 0. So z minus 1 is a factor by the factor theorem. And we really should say that when we use it. It's kind of not plagiarizing someone's work, right? So we give credit to the factor theorem. Now, that's still going to leave me with a quartic. And I'm not seeing any nice pattern. So I might go on and go, okay, I've got one factor. Let's keep going and see if we can get a few more out. So the next number that I'm going to try is p of negative 1. We'll see if z plus 1 is a factor. So we get negative 1 plus 6, so minus negative 6, minus 2, minus 17, minus 10. So this is not looking anywhere near as good because I can see that I've got negative 3, negative 20, negative 30, negative 24. So no good, or not a factor. I'm going to try a couple more. Also, if you're doing this in an exam situation, the factors are almost always going to be, at least to start with, nice integer values. So we'll try 2. And we're going to get 32 minus 6 times 8 minus 2 times 4 plus 17 twos, 34, take away 10. Right, what have I got? Well, I've got 66 minus 48 here, minus 18. Yay, I've got 0. So z minus 2 is a factor. Now that means I'm going to get down to the quintic being the product of a quadratic from those two factors and then a cubic. And that's probably as far as I'd go. You could keep on going and do a bit more guess and checking, but eventually you're going to hit some complex roots. So it's up to you really when you kind of stop and start the harder part. So let's write it out now. What have we got? Well, we've got z to the 5, so the polynomial on this side, and it equals z minus 1 times z minus 2 times a cubic. So the most useful way to work here is to multiply this bit out and say, well, I've got z squared minus 3z plus 2. And let's think about what that cubic's going to have to be, because some of it I can do immediately by inspection. Well, if I'm going to have z to the power of 5, this must be z cubed. Then I'm going to have a yucky couple of terms that I have to do a bit more work on. So az squared plus bz, or whatever you want to call these. But then the constant is going to be easy, right? Because it has to equal negative 10. So over here I'll go minus 5. Right, now we're going to match coefficients. The easiest way to do that, well, you can pick whichever ones you want. We've got no x to the power of 4 term. So we've got 0 z to the power of 4. And let's look in here at where the z to the power of 4 terms are going to come from. Well, I'm going to have one here. So that's a z to the power of 4. I'm going to have another one coming here. So this times this, so minus 3z to the power of 4. And that's going to be it. I'm not going to get a z to the power of 4 combining from the 2 and anything over there. So that tells me that A must equal 3. Now, where does that leave us? Well, we've got to do another match. So I'm going to pick the 17z. We'll match the z terms. So 17z is equal to, let me just erase that stuff there. Now let's do it again. 17z is coming out of 2bz plus 15z. Right? And the more you practice this, the faster you'll get at doing a matchup. What does that mean? Well, that's a really easy one as well. That tells me that b is equal to 1. So it hasn't finished my problem, but now I've got a cubic that I have to factorize, and so off I go again. So let's call the cubic something. Now we've used up p of z, so we're going to call the cubic q of z, and we're going to factorize this. So q of z is equal to z cubed plus 3z squared plus z minus 5. Right, what are we going to do? Well, even just by writing that out, you might have got a feel for what's going to give me a factor. So factor theorem again. Let's go back and try 1. Well, we've got 1 plus 3 plus 1 minus 5 equals 0. So z minus 1 is a factor. Now, some of you are probably going, oh, hang on, we already had that. What is she talking about? Well, what we've got is an example of a repeated root. So now, if we go back to p of z, my whole polynomial, which was the z to the power of 5 thing, we already had that was z minus 1 times z minus 2 times my cubic. Right? But now what we're saying is that that cubic can be written as z minus 1 times a quadratic. So factorizing q of z goes like this. Z cubed plus 3z squared plus z take away 5 is equal to z take away 1 times z squared. Leave this bit here. To get minus 5 here, we must have plus 5. So let's call that just kz. We're going to match again. Let's see. Match on the 3z squared. 3z squared must come from this negative z squared plus kz squared coming from in here. So k equals... Okay, so k equals 4. Something weird just happened to the recording. Sorry about that. So that leaves me here that now I've got to go and factorize this quadratic. So let's do that. So z squared plus 4z plus 5. I'm going to do this again using the sum of two squares. So I get z plus 2 squared, take away 4 plus 5, which is z plus 2 squared plus 1. Factorizing that gives me z plus 2 plus I times z plus 2 minus I. So now we can put all of that back together and we've got our roots. So p of z is equal to z minus 1 times z minus 2, the first two that we got out of the factor theorem, times z minus 1 again, times z plus 2 plus I, times z plus 2 minus I, which is equal to z minus 1 squared times z minus 2, z plus 2 minus I, z plus 2 plus I. So the roots are what? Let's see. 1, so the roots are 1, and we're going to say repeated. 2, and then negative 2 minus I, and negative 2 plus I. Now we don't want to leave them like that. Okay. So 1, 2, negative 2 plus I, negative 2 minus I. So there you go. So that's one approach for factoring quite a high order polynomial. You just start with the factor theorem and move through. One more thing I wanted to say. I know that some of you will be going, I really didn't like how she factorized that using completing the square. You don't have to. You can go and factorize that if you want to using the quadratic formula. Okay, so z squared plus 4z plus 5 equals 0. Z equals -4 plus or minus blah 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 blah, and you'll pop out with these two roots. Okay, and if you want to do it that way, that's fine too. I do think it's worth getting comfortable with this method because it's going to help you whenever you've got this kind of quadratic embedded in a harder problem. Thanks for watching. I've got a couple more videos to come. We probably won't get through all of them in class though.